Hello, the predictive task I'll be studying today is basically just classifying biomes from the game Minecraft. To start off, what even is this? When you play Minecraft, your machine will generate some infinite open world that consists of many biomes, like the one pictured right here. We have some jungle picture, a savanna picture, and a frozen ocean picture. These biomes have distinctive features that can be identified, but not all pictures will be the same because it is a procedurally generated world and is generated randomly. And given this biome classification, it does change the way you play the game because each biome has unique resources and landscape that could be fed into a machine learning model to let the model learn how to play the game. And all of these are pretty easily identifiable, but this task is not trivial. I'll show you a few difficult ones right here. We have a frozen ocean and frozen river. Those are going to be very difficult to differentiate. And this flower forest and forest right here. And to assess the validity of predictions, there is a feature in the game to identify the biome. For example, this is a snowy plains biome. So we do in fact have all the answers, but I would like to be able to identify the biome without this external help. So now I'll be showcasing the data collection part of this project. To start, I'm gonna run this command right here, which will put me in a random location inside of a 1 million block radius. As you can see, I'm in a different place now. I'm on a beach, as you can see on the top left. It'll tell me the biome I'm in. But when I start taking screenshots of this, I'm not going to really want that information as it's going to give identifying information about the biome. So when I take a screenshot, I'm going to hide this information like so. As you can see, the information at the top is gone. And I'm going to take 4 screenshots like so. One right here, one right here, one right here, and one right here. And these will all be classified under the beach biome, even though like this screenshot right here will have a lot of green. I'm pretty sure this is a plains biome right here. This is because I'm going to be standing on this block, which is still a beach. But to classify the images, since I've hidden the information at the top, before taking screenshots, I'm also going to run this command, which will put the biome name inside of chat, so that I will classify the images later using another script. But I'm going to do it once more just so you get the idea of how I'm going to take these data collection. So I'm in a new place now. I'm going to hide this information, take a screenshot right here, one right here, here, and here. And also run this command again so that I know I'm in a forest, and then repeat on and on. I'm going to show off the script I have to take screenshots really quickly. So first of all, these 2 functions are going to be the just helper functions, just so I can run the chat commands. Right here, this is the cycle I'm going to be running. First of all, I have to locate the Minecraft window, which will be right here. Next, I'm going to try to cut out, when I take the screenshot, I'm going to try to cut out this top border right here that says Minecraft. That's just useless information that I don't want. So to start, like I said, I'll be teleporting in a random place. I'll actually have to wait 10 seconds just so my computer can generate the blocks and load in the world. I'll be cutting out this the border in the screenshot so that I don't get the top portion. And I'll be taking the screenshot with a date and time attached to it so that I can identify the biome later. But right now, the screenshots will just have a date and time attached to it. And finally, I'll be running this a whole bunch of times. As you can see, I have you can set the delay count and where the screenshots are stored. Once I take the screenshots, they'll be in these folders. They'll kind of look like these pictures. And I'll want to classify these images, but there's no information in the screenshot itself. But we'll look to the file name for example, it'll be in the format shot and then a number and then a date and time. As you can see, I took this image on November 22nd at 3:16 a.m. I'll have to look through a logs folder. I'll have to iterate through a folder like this. Look for these chat messages. As you can see, if I took a screenshot at this time at 3:36 p.m., then I'll know that those screenshots are of the category beach, and this one will be at the forest. And I'll have to basically do this for every single image and classify it that way. And I'll put it inside this sorted folder, which will contain all of the sorted images. And I'll show off that script right now. This is basically just iterating through, like I said, using some patterns to classify the biomes. And this is just reading the log and determining the closest message of this format. The forest, we want to ignore the other messages because those are not important to us. We'll look for the beach, river, and etc. This is just determining the date and time of the image and processing it and then moving it to the designated folder. Once we've collected the screenshots and sorted them into these various 47 folders, I'm going to start by doing some exploratory data analysis. First off, we've taken these images and sorted them in descending order for each folder. As you can see, most of our images are going to be clustered in this forests and plains folder, which have around 1,400 images per folder. And as you can see, there's a level off as we find the less common biomes. The biomes down here, they're still going to have a handful of images per folder, but the bar is just so low you won't be able to see it. We'll scroll down. We can see the average color by biome. I just iterated through every image and found the average color. And some of these greens are going to be hard to differentiate between. That's going to be the big struggle in this test. But some of these blues, like this vibrant blue right here, it's going to be quite easy to classify. We'll know what that is off a first glance. To look a little bit further, I took the top 10 common biomes, and we're looking now at the average RGB component. And this just gives a little bit better look at what kind of colors we're looking at here. And to get a little bit of a deeper look, now I'm looking at the top 5 biomes, but I'm giving an RGB histogram so that we can see what colors are going to be most common for each of the RGB components. See plains right here. These are all going to have pretty different histograms so that we'll have a better idea of what to look at for each biome. That concludes the data exploration part of my project. I proceed with the modeling part of the project, and to start, the inputs for the problem will be the pictures of the biomes themselves, and the outputs will be the biome name. To optimize, I would like to optimize the information I can glean from these images, such as the features that I get. And the decision I have to make is take a classical approach or a machine learning approach. And based on the models from this class, I'm going to really look at the classical programming approach to solve this task. However, later I will showcase some machine learning approaches. Some advantages to using a classical approach is utilizing feature engineering to my advantage, as well as it being less computationally expensive compared to training a model. I would likely choose machine learning if I couldn't use my prior knowledge of the game to manually design features, or if the pictures were so complex that I couldn't use simple statistics. I don't think this is the case, however, so I will be proceeding with classical learning approach. To give a brief overview of the architecture of our project, I'll be looking at the data we have. We have a data folder filled with folders of each biome, and these folders will just contain screenshots of each biome, such as this birch forest folder right here. And so this makes it easy because we actually do have all the answers to the screenshots we have that we want to identify. So that makes our validation portion easy. And also I'll be looking at a code portion of one of our models. First we have a configuration section and also a feature vector function to extract the features from the images. Then basically we're going to iterate through the data folder I mentioned earlier, and we'll be extracting every image from this set and extracting also the feature vector from that. Then we split it up into a train and test split with an 80-20 split. Then we train our model, and now we're going to try to predict and see the accuracy on the test set. And the rest of the code is just finding misclassified images so that we can look for future improvements, and it's just going to output this with a validation accuracy right here. Next, we proceed with the evaluation part of the project, and to be clear, our models will solely be evaluated on test accuracy, aka the percentage of images that are correctly predicted. To start off, we have some baseline models, a random classifier, aka taking in any image and guessing some random biome, will achieve about 1 in 47 or 2.1% accuracy. Guessing the most common biome, which is forest, will get us a little bit further. It should get 19% accuracy because it consists of about 19% of the world. And then picture to the right here is just a pre-trained neural network, and training it on our data set will give us an 82% accuracy. And so that's going to be the number we're looking to surpass. Next up, the first idea we have is to look at the average color of a screenshot. Up here we have a graph of every biome and the average color in that biome. And now to classify pictures like this, we can find the average color of all the pixels, which is about this color, and then now find the closest color to this biome and then predict that. This is not going to be a very good start, and this will only get 10% accuracy, but we will see huge improvements soon. To motivate this improvement, we're going to take a look at the same screenshot and notice that the top, maybe 30% of the image is just sky and clouds. This is not going to be differentiating information, as most screenshots will have this sky, so we can cut off the top percentage of the screenshot to get a better accuracy. And this does show, because if you look at this graph right here, all the average colors are going to be muted, but if you cut off the top half of the screenshot, then these colors are going to become much more vibrant and easy to differentiate, and this will actually raise our prediction percentage to 23%. For the average color model, we'll look at the K nearest neighbors, and to motivate this, I looked at the top 5 predictions of the screenshots that were incorrectly predicted, and I noticed that even though the top prediction wasn't correct, the true correct prediction was indeed in the top 5. So I could now look at the K nearest neighbors to the screenshot, find the closest images, and predict the majority biome. And iterating over many K, I found that K equals 9 is the best one. So now for every image, like this jungle one right here, I'm going to look at the nearest 9 images in the training set, and now I'm going to predict the majority predicted biome for that. And this does result in a 54% accuracy, which is a huge increase. Next up, instead of one feature, now we're going to be using 16 features for each color to better capture the minute changes of color between the grasses and trees. And now we're looking at this histogram to motivate this change. And using logistic regression, this does get us an 80% accuracy, which is very close to the neural network we saw earlier. To analyze some misclassified images, we can see that this model still struggles with minute changes in color. So to motivate the next change, I'm going to be adding more bits to the histograms that we're going to be looking at. So instead of 48 features, now we're looking at 380 features, and this does work and increases their accuracy up to 87%. For my final model, I tried to squeeze out a little bit more accuracy from the testing set, and so I looked to adding HSV histograms, that is hue, saturation, value. And as you can see, those histograms will differ from the RGB histograms that we can see up here. We're going to see some different distributions for the same biome so that we can classify them better. And I'll be also looking to add 128 bins for each of the RGB and HSV so we can double our features and get a little bit more accuracy. This does jump our accuracy to 88.7, up from 87%. Now I'm looking at some metrics of the final model. Here we're looking at the per class accuracy versus the test class size. As we can see, the majority of biomes are going to be clustered in this upper left quadrant, which is a big success for us. As we can see, we're struggling a little bit on some biomes with low test samples, such as the flower forest. We're going to be confusing that a lot with the regular forest and savanna plateau with regular savanna, and also sunflower plains with just the plains. We also do well on these plains and forests, which makes up maybe 30% of the data set, so that's also a big success. Up next, we have a graph of accuracy like we saw before, but also we're looking at F1 score. Since these two charts correlate pretty well with each other, we can see that our model is doing well on the common classes as well as the less common classes. So we have good generalization for all biomes, and our model is not going to trip up if we see a less common biome. Finally, for some self-reassurance, we're looking at some specific examples of misclassified biomes. As you can see, the T is true and P is predicted, and our predicted biomes aren't so far off of the true prediction. For example, these images were all sunflower plains, but we predicted them as plains. And even in this third image, there's not actually a sunflower visible, so I would say our model is actually correct there. It's very difficult to differentiate between these cases, and we'll see some more images right here. This model is not able to identify the flower forest, and to be honest, I can't really see any flowers in some of these. That's a flower right there. And in the last one, we are confusing this savanna plateau for a savanna, and admittedly, I don't actually know the difference, so I couldn't do better. And that is that for the metrics for the final model. To begin the discussion part of our section, I will note that there's really only... To begin the discussion part of the project, I will begin by noting there's only one real project done on this otherwise, and that is Willow's biome detector repository on GitHub. We do both start by collecting our own data on the latest version, so we're going to have different data sets. And I'll also note that their photos are going to be of lower quality, and I'll elaborate on why in the next slide. But as you can see, my screenshots are going to have much more clarity to them than his screenshots. We did take different approaches to this task. I took a classical route, whereas they went for a machine learning approach. This is also likely why they resized their images down to a lower quality, because training these neural networks are going to be very computationally intensive. They trained multiple models, but none of which are able to score above 80%. Earlier, I was able to show that a pre-trained neural network will get you up to an 82% accuracy, but I was not able to approach a 90% range, and I do think that you wouldn't be able to without significant work. I'll take a little bit more in-depth look at their best model, which is the cross-entropy loss. They're basically using this to measure how surprised the model is to see the true label of a class, but training with these large class size imbalances will lead to heavy overfitting. As you can see in this top graph right here, most of the classes right here are going to be having a 100% accuracy, but on the testing set, a lot of these smaller class sizes will drop drastically. And so those classes will have a below 20% accuracy, and it does average out to a 73% testing accuracy, however. I will finally note that they did do their project 2 years ago, so their model would be alright on the modern versions of Minecraft, but our models are also not going to be directly comparable due to the version changes. I am confident, however, in the classical programming approach, as surpassing that 80% mark with my model does cement my model as the best biome classifier. And with that being said, I would like to thank you for your time, and I hope you all have a great rest of your quarter.